In the last video, we talked about roots and zeros of polynomials. And along the line, we got to a point where we talked about multiplicity. And I think it's important that in this video, we go into a bit of depth talking about multiplicity of polynomial roots. We already have some concepts in place based on the last video, but here, let's go deeper, right? Multiplicity of roots describes how many times a root is repeated in a polynomial and how this repetition affects both the algebraic factorization of the polynomial and the behavior of its graph near that root. In particular, we have odd multiplicity. So here now, we're looking at multiplicity and how it also affects the behavior of the graph. And I mean, in the last video, I showed you, we solved, I think, a simple equation, x squared minus 5x plus 6. And we saw that the solutions are 2 and 3, which makes the graph to cut the x-axis at points 2 and 3, like that. But when we had repeated with, like, we had x minus 1 squared. So we have the graph just touching 1. If it is x minus 2 squared equals 0, we have the graph touching 2, and it keeps going like that. So we have odd multiplicity, the graph crosses the x-axis, and we have even multiplicity where the graph touches and turns at the x-axis. And that's the classic example I gave you about x squared minus 5x plus 6 equals 0. That talks about odd multiplicity. And you have even multiplicity where the graph just touches and turns at the x-axis. Okay, so let's talk about definition of multiplicity. Of course, we've said it already, but let's look at it in some more depth, like I said. So definition of multiplicity. Let P of x be a polynomial and let R be a real or complex number. So we say R is a root of P of x with multiplicity m if x minus R raised power m is a factor of P of x. And then we say x minus R raised power m plus 1 is not a factor of P of x. So equivalently, there exists a polynomial Q of x such that P of x is equal to x minus R raised power m. So it means that this linear factor appears m times multiplied by whatever is now left after you factorize this out. That's Q of x. So we now say with Q of R not equal to 0. So if Q of R is equal to 0, of course, everything else breaks down, right? So if M is equal to 1, then we say R is called a simple root. And most of what we've been getting so far are simple roots. When you just solve like, when you solve x squared minus 5x plus 6 and you get 2 and 3, those are simple roots. But if M is greater than or equal to 2, then R is called a multiple or repeated root. So in the case of, I think that should be x squared minus 2x plus 1. So, and you get is a result of minus 1. You know, we have minus 1 twice. That's a repeated root like that. Okay, so here we see another example. So you have x minus 2 raised to power 3, x plus 1 raised to power 2. Of course, this is something we have come across a lot. We already know this one has been factored for, so thankfully, we don't have to go through the stress of trying values to see which one is a root or which is not. So of course, clearly, if you equate this to 0, we are going to get x minus 2 cubed raised to power 0 and x plus 1 squared raised to power 0. So that means we get x raised to power x equals 2 3 times, and we get x equals minus 1 2 times. So x is equal to 2 is a root of multiplicity 3. X is equal to minus 1 is a root of multiplicity 2. Okay, so here the exponents of the linear factors give the multiplicities of the corresponding roots. So can we try to plot that? I think, are we talking about the graph yet? Okay, yeah, let me just talk about the graph in case I'll just mention it and keep going. Okay, so we are trying to plot on Desmos now. Desmos is really very useful and handy. X minus 2 cubed, x plus 1 squared. Okay, x minus 2 cubed into x minus 1 squared. Now, so you see, we have 1 2 times. So you see that it just smoothly goes through 1, but we have 2 like 3 times. So you see it's we have a kind of movement happening around all these whole places. Okay, yeah, equals 0. It's not necessary. Okay, that's not necessary now. So we just see all those. So we need to zoom in to see stuff. So you can see this. So you can see just touches 1. So if you zoom in better, you see just touches 1 at that point. But when you come, then here it cuts, it comes down, and then at 2, we also have it there that way. Okay. So we'll learn more things about behaviors like that as we keep going. In 12.2, now we talk about multiplicity and the total number of roots. So I think we made mention of something like this in the last video, but it's good to look at it again. So let P of X be a polynomial of degree n. So the total number of roots counting multiplicity is at most n. So the number of degrees, the degree of the polynomial tells you the number of roots you're going to get. So for a linear polynomial, you get one result. For a quadratic polynomial, because the power is 2, you get two solutions, two roots. For a cubic polynomial, because the degree is 3, you get 3 roots. For a quartic, you get 4, quintic, you get 5, and so on and so forth. So for a polynomial of order 10, of degree 10, you get 10 solutions, 10 roots. So over the complex number C, the fundamental theorem of algebra guarantees exactly n roots counted with multiplicity. So if P of X can be expressed as A into X minus R1 raised to power n plus 1, X minus R2 raised to power n plus 2, and so on up to X minus RK raised to power n plus K, with A not equal to 0. I mean, once A is 0, everything breaks down. Then we say that m plus 1, m1 plus m2 up to m plus k is less than or equal to n, okay? And the sum equals n, where all complex roots are included, counting multiplicity, basically, right? So that's the idea of multiplicity involving and the total number of roots. Now, talking about 12.3, in 12.3 now we talk about graph behavior and multiplicity. We're looking at it in a qualitative sense now. So we study the graph of y equals p of x. That's a polynomial solved solved like that near a root x equals r of multiplicity m. Since p of x is equal to x minus r raised by m multiplied by a particular q of x, so with q of r not 0, then near x equals r, the graph behaves like y is approximately some c multiplied by x minus rm, where c equals qr is a non-zero constant, right? So the key idea is this: the parity of m, whether it is odd or even, determines whether the graph crosses or touches the x-axis at x equals r. So the size of m controls how flat the graph is at x equals r. So the flatness is determined by m, and the parity determines whether the graph crosses, whether if it's odd or even, it crosses or it touches. And I give you a very simple example of x squared x raised to power 2 minus 5x plus 6 equals 0. So clearly the solutions, okay, let me just leave it this way then. So clearly you see the solutions at 1, 3, so they cross at that point. But what if we now have x minus 1 squared, x minus 1 raised to power 2, raised to power 2. So you see this one, instead of this one crosses, but this one just touches. And that's what we mean by this. So the parity of m, odd or even, determines whether the graph crosses. So odd crosses, even touches, okay? So the size of m controls how flat the graph is at x equals r. So in this case now, look at this x minus 1 is raised to power 2. So see how it is. So what if we change it to x minus 1 raised to power 3? So you see it touches, so it's the curve keeps branching out like that. What if we now have x minus 1 raised to power 4, so you see it comes back again, and then it just keeps, but the key thing is that it keeps touching that way, and so on and so forth. So there's a behavior that we get to see. So we talk about odd multiplicity, which I mean, I've given you an example of that already in talking about x minus 5x plus 6. So odd multiplicity, graph crosses the x-axis. So suppose m is odd, that is m is 1, 3, or 5. So then x minus r raised by m changes sign as x passes through r. So it changes sign. So for x less than r, so we have x minus r raised by m has one sign. For x greater than r, so we have x minus r raised by m has the opposite sign. So thus, provided c is q of r is not equal to 0, the sign of p of x changes across x equals r. In conclusion, if the multiplicity of R is odd, the graph of Y equals P of X crosses the x-axis at x equals R, which I've shown you already. So we have this simple example, simple odd multiplicity where M equals 1. So let P of X be X minus 1, X plus 2. So we have root at X equals 1 multiplicity 1, root at X equals minus 1, minus 2 with multiplicity 1. So at both X equals 1 and X equals minus 2, when you solve this, the graph actually crosses the x-axis. Locally, the graph behaves like a non-horizontal line cutting through the x-axis. So x minus 1, x plus 2 now. X minus 1, okay, into x plus 2. X minus 1, x plus 2. So again, you see, it cuts at minus 2 and cuts at 1. That's exactly what we are talking about. Okay, so example 3 now. When we talk about high order odd multiplicity, high order odd multiplicity, okay? So let P of X be X minus 2 raised to power 3 now. So root at X is equal to 2 with multiplicity 3, which is odd. So the graph of Y equals X minus 2 raised to power 3 still crosses the X-axis at X equals 2, but the crossing is flatter, all right, than in the simple root case. So summary for odd multiplicity is just that odd multiplicity implies that graph crosses the X-axis. Larger odd multiplicity crossing is flatter and less steep. So we see like for x minus 2 cubed, right? That's x minus 2 raised to power 3. So x minus 2 raised to power 3. So you see that. Let's even start. Okay, this is raised to power x minus 2 raised to power 1. Raised to power 1. Oh, okay. I mean, just it's cut like that, right? Uh, so we have 2 now, it just touches. Then for 3, which is the emphasis now, we have 3, so it gets smoother. So I guess we can get rid of this. Then we have this now. Instead of 3, it now goes to 5. 5. So it just keeps getting smoother and smoother like that. Okay, so we go for even multiplicity. Okay, I think I already dabbled into that, kind of. So even multiplicity now talks about even multiplicity. So graph touches and turns. So for odd multiplicity, we said that the graph crosses the x-axis. For even multiplicity, the graph touches and turns. I think I'm going too far away from here. Okay, I can take it with the example, right? Yes. So suppose m is even, that is m is 2, 4, 6, then x minus r raised to power m does not change sign as x passes through r. So for x less than r and x greater than r, x minus r raised to power m has the same sign, non-negative, because it's positive, it's even, right? Even if it is minus, the minus is swallowed up, it becomes positive all the way. So it has the same sign, non-negative if m is even and the base is real. Thus, if c is q of r equal is not 0, the sign of p of x remains the same on both sides of x equals r. In conclusion, if the multiplicity of r is even, the graph of y equals p of x touches the x-axis at x equals r and then turns back without crossing. So example 4, simple even multiplicity, you have m equals 2. Like that case of x minus 1 equals x minus 1 squared, equate to 0, you get x equals 1 twice. So root at x equals 1 with multiplicity 2. So the graph of y is x minus 1 squared, and it touches the x-axis at x equals 1, then turns back up since the coefficient is positive, right? So looks like a shifted upward opening parabola. So basically x squared or anything x minus something squared like that would be a parabola. Here, the sign of p of x is non-negative on both sides of x equals 1. And it is because the power is even. Even if you throw in a minus there, the evenness makes it positive again. So that's exactly what's this one now? X minus 1 all squared. X minus 1 squared. this. So you just see it touching that one right there. So it comes and then switches over. So let's see what happens for 4 now. You see, it just opens up more like into a bowl. So it keeps going like that, because it just touches that. So you can see it's flattening out as the power increases. 6 now. So it just keeps flattening out better and better like that. So example 5 now. Example 5. If we talk about example 5, higher even multiplicity. I think I already did that. Like when I used 4 and 6, you see it's flattening out. So higher even multiplicity, m equals 4, for instance. So let p of x be minus x plus 3 raised to power 4. So the root at x, okay, the root at x is minus 3 with multiplicity 4, which is even. So the graph touches the x-axis at x equals minus 3. So the minus here is because of this minus. So you can see 4 is not affecting it. So touches the x-axis at x equals minus 3. This then turns back downwards because of the negative coefficient. So this negative here is what's causing that. So the contact to the x-axis is very flat. As you can see, as the power increases, so this one is sharp, then the next one is flatter, the next one is even flatter, and so on and so forth. So the contact with the x-axis is very flat, more so than a simple parabola. So summary for even multiplicity. Even multiplicity implies that graph touches and turns at the x-axis. Larger even multiplicity implies that the graph is flatter at the point of contact. So let's try out this minus x plus 3 raised to power 4 thing and see how it goes. Minus x plus 3 raised to power 4. So, you can see that now. The minus is what makes it turn in the opposite direction. And so if we increase this now, the flatness increases. So it's flatter with power 6. So it's more flattened out. So like that. So in summary, visual summary for qualitative shapes now. Okay, I've shown you all of these things on the graph directly. So at root x equals r of multiplicity m is equal to 1, that is odd. So the graph crosses the x-axis with a shape similar to a non-horizontal line. Then m equals 2 is even, graph touches and turns, parabola-like behavior near x equals r. When m is 3, which is odd, graph crosses but with a flatter cubic-like shape, right? When m is equal to 4, which is even, graph touches and turns, very flat, quartic-like behavior. I've shown you all of that. So the key idea is that as the multiplicity m increases, the graph becomes flatter near the root, basically. Okay, so we have a summary table to drive the point home. So in summary, trying to maximize my space. Okay, yeah. Something like this. In summary, for sure, summary table, multiplicity versus graph behavior. So multiplicity m, if m is 1, the parity is odd, the sign change is yes. So there's sign change for all odd, and there's no sign change for all even, basically. So for x equals 1, it crosses the x-axis with a simple crossing. That's the graph behavior at x equals r. So sign changing at x equals r, those are the things we have here. For 2, the parity is even, the sign change is no, and it touches and turns, parabola-like. At 3, the parity is odd, the sign change is yes. Then graph behavior crosses, cubic-like and flatter. Then at 4, when m is 4, the parity is even, the sign change is no, and it touches and turns, quartic-like. So it touches and turns and it's flatter. So any odd is odd parity, sign change is yes. Then graph behavior crosses x-axis, any even at all. Even parity, there is no sign change at x equals r, and it touches and turns on the x-axis at x equals r. Okay, so you can, I've tried out all these plots all along, so you want to try this ones too. List each root of its multiplicity. This is x equals 2 with multiplicity 2, then x equals minus 1 with multiplicity 1, basically. Okay, describe the graph behavior at each root. So because this is even now, it is going to just touch it at 2, and this one is going to cross at minus 1. So x minus 2 squared, x plus 1. Okay, x minus 2 squared, x minus 2 squared into x plus 1. Okay, so you see that it touches at 2 and turns, but 1 just it crosses at 1 right here. So as you can see, all of that. So that's the deal right there. Okay, so you can try out. I mean, once you have internet, you can use Desmos. You can just go to desmos.com. You don't even need to sign up for anything. So just plot your graph directly, so that makes life easier. I think I want to try that question 3, which talks about uh, p of x equals x raised to power 5, x minus 4 squared. Of course, in this case now, since x is equal to 0 5 times, that's what this means. What is the degree of p of x? Of course, that will be 5 plus 2, 7. So the degree of this is 7. You add the powers together. Then find the multiplicity of each root. 0 5 times, 4 2 times. That's what this means. Describe the local behavior of the graph at x equals 0 and x equals 4. Of course, at x equals 0, because the power is odd, you're going to have a turn, you're going to have you're going to have a cross through that point. At x is equals 4, you're going to have a turning. So it touches at 4 and it turns. So let's try it out. X raised to power 5, x minus 4 squared. Okay, x raised to power 5, then x minus 4 raised to power 2. So you can see that already. So you see that at 4, it just touches and turns, as you can see there. But at x equals 0 now, so you see the flat touch, just passes through like that. So because x raised to power 5 is x raised power, if you equate this to 0, so you get x raised power 5 equals 0. That means x is equals to 0 5 times, and x minus 4 squared equals 0. That x equals 4 2 times, basically. Okay, so you can try out other questions. Okay, let me see if I can show the 5 questions at once. I think it's harder to do that. Okay, yeah, these are all the 5 questions. Thank you so much for listening to this very interesting video about multiplicity of polynomial roots and graph behavior for that matter. Okay, so thank you so much. Let me know how helpful this is for you. Okay, something else you'd like me to talk about, feel free to let me know. If you have subscribed already, I thank you very much. If you have not subscribed, of course, you want to do that right away. And hit the notification bell so you can always get alerted each time a new video is released. Having done that, you definitely want to become a member of this channel, as much as possible. And that gives you some special privileges. At the very peak of that privilege, of course, you have privileges like maybe some videos are specially made for members. Members get at the first to see some certain videos before the other people see it. At the very highest level of that, we can hang out physically if you're in the same geographical location. And we can also hang out online to talk about anything that interests you on my channel, be it mathematics, anything related to mathematics, data analysis, data science, machine learning, scholarships, writing books, all those things. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on this channel. Till I come your way again, keep doing math right. Bye.